Yeah, thank you very much for the introduction. Yeah, we'll do this in like alternating. So I'll start with telling you kind of, because I joined the Ethereum Foundation pretty recently. So I'll try to tell you like some high-level overview of everything that I wish I had known like a year ago. So we'll start with this, and then Francesco will go a little bit more into the details, actually much more into the details of all the systems aspects of all the amazing things that he's created over the past years. Yeah, trying to like, I guess, maybe getting inspirations of open problems that are left and like, models that we can improve. And then at the end, I'll try to loop back and talk a bit about what's the future for, how the future for Ethereum consensus could look like. And so, yeah, just to start, oh yeah. So sometimes I think, I understand what's going on. And then I'll suggest something to Francesco or to Roberto and Luca. No, sorry. Cool, thanks. Yeah, so sometimes I think I understand what's going on, and then I ask a question or like I suggest something to Francesco. And then there's always, every day or every week at least, there's something new that comes up. It's like, oh, okay, maybe not a bad idea. So, but have you thought of the inactivity leak? This is not going to work with the inactivity leak. Or oh, but we want dynamic availability, and then have you thought about the healing from asynchrony? Or oh, this is going to use way too much memory. We have to be mindful. We have 1 million validators, so the beacon state would explode if we did something like this, right? Or oh, the votes have to be on chain. All these kind of real life problems that come with it. Oh. All right. So so Francesco will tell you more about all these things, but I'll start with more like a historical overview of the past and kind of the more practical aspects of Ethereum. So of course we want to build a secure distributed system, so that if one node crashes, for example, we can still produce more blocks and we can still be happy. Now, if you had only one code, one client implementation, then what could happen is that you could have a bug, and then potentially all of them would crash, and you'd be pretty unhappy. And so Ethereum has this kind of, I think, pretty unique thing of having many different client implementations. And so now if one client has a bug, we can still finalize, and actually from the outside it looks like nothing ever happened. This is a pretty, yes?
Sorry, I'm already confused actually. Client or validator? How do you define it?
Oh yeah, I'll have a slide, but yeah. So the validators are run by clients. That's kind of the. Sorry, validators. the clients is the whole software that talks to the other clients, and on top of a client, there's another piece of software that runs a validator, okay. Or that runs that has a private key, and that signs.
Cool.
Yeah. Does that make sense?
No, yeah, go ahead.
Yeah, I'll try to stick with client and validator and to notice kind of when you conflate both, I guess.
Cool.
So yeah, this happened pretty recently, last year, where in the latest hard fork, one client had a bug. I think it was replaying some history too much or something like this, and essentially DOSed itself. And so you could see the share that this client had by seeing just how much voting participation dropped. But it happened that this client had 25% of the share of the validators, and so finality kept progressing without a problem. However, what would happen now if there's bugs in multiple clients, for example, right? Then we would actually be in a situation where we lose finality, which would make us pretty unhappy. This is also not too far-fetched. Also happened last year, luckily only on a testnet. But actually this time it was not. So these are the little icons are for the consensus clients. Ethereum also has execution clients. So this bug particularly was on the execution clients. So you can pair any consensus client with any execution client. And so 3 of the execution clients accepted invalid blocks. And so this made it so that it turned out that more than a third of the validators were running using these execution clients that were faulty. And so they dropped, and they didn't, actually they even there was a super majority, so they even finalized something that was invalid. And so the recovery from this, we can talk about it maybe later with the inactivity leak, but eventually actually the ones that had not done something wrong, they recovered finality through the inactivity leak. All right, and so for this case, Ethereum actually wants to have a fallback mechanism. Itai called it like wartime, peacetime mode. And so wouldn't it be nice if we're in this situation of having a lot of crashes, if we could still produce blocks and still have kind of progress? This is, you could say, okay, it could be good for throughput. You could say, I'll try to argue that it's good just to limit the chaos that happens. So if you can still add, like, even if you have multiple of these fallback chains, they might not be safe, right? But you can still add all the real world updates on that chain. So you can still, for example, follow the markets. And so by the time you resolve your client bugs and you start finalizing again, you can link back to that fallback, and all the markets can be already in good condition. We could even go a bit further and say, okay, actually, even in that fallback mode, you actually might want to provide some security guarantees. So maybe have a different signal here, and that signal might be good enough if you want to buy coffee or probably even do most of your transactions actually. So that's kind of the give you a little bit of a teaser of what's to come. So Ethereum started, of course, with proof of work. So we had a great talk yesterday about proof of work, so I'll not go too much into detail. I just stole this snippet from Roger's slides from his lecture. So in proof of work, essentially you could say, okay, it's a function, you give it a challenge and a nonce, and it returns whether you can produce a new block or not. And so if you successfully solve that challenge, you can append your block, and you're happy. And of course, you follow the chain with the most amount of work done. Ethereum, I'm just mentioning this because I want to introduce kind of Ghost, just greedy heaviest observed subtree. And so this is kind of a variant of the proof of work we've heard yesterday, where in your fork choice, so it's based on Jonathan Sampolinsky and David Zahar's work. And in the fork choice, which is a term that I think will come up later, the fork choice is how you follow, when you start from the chain, the blocks you've observed, how can you reach the tip of your chain? And so in Ghost, you would follow the whole, so you'd consider the whole subtree, and so the sum of work over the whole subtree. So here you'd go to this block. And so at the end, this would be the tip of your chain. So this has some good properties. We've heard yesterday, I think, at the end of the talk, what happens if there's a lot of stale blocks. So this is one way to kind of improve this. The other thing is what happens for decentralization. If you have a lot of small stakers, you want to support them. One thing you can do is you can include all the uncles and reward the uncles also for their work. This is something that was done in Ethereum proof of work. All right, but really what's left of this today is the sleepy model. Yes?
Sorry. How did you make this magic with you showed the slide, then you went back, and then you didn't show the slide again?
And then I what?
You had the paper slide that you showed it, right? And then you went back, then you never showed it again. Oh, it was the same slide.
I think I just had a rogue slide in there.
Okay. Nice. Sorry.
Yeah, it was magic.
Consider you're paying attention.
All on purpose. But what we inherit from this proof of work essentially is this the sleepy model. So this very nice property actually, that even if we have varying participation, so if we consider that nodes or validators later on, if they go offline or they temporarily are asleep, we can still provide safety as long as 50% or less than 50% of the ones that are still awake are honest. Okay, so there's two things that we want here. We can still build a chain if at least one validator is honest, is awake, and if we have less than 50% Byzantine. So we'll come back to that quite a lot. So far, I would say we have mostly seen this model, the standard partially synchronous BFT model. But Ethereum also wants to combine it with this sleepy model, which the stronger assumption is that we require synchrony. So we'll have two chains. You'll see there's a finality chain and an available chain. From the available chain, we want to have this higher resilience. We want to have the property of only needing one awake. And from the finality chain, essentially, we want the economic security. Right, so at some point then, Ethereum decided to switch to proof of stake. One consideration you have to do then is, okay, well, how do we solve Sybil resilience? So this was done through staking. Initially, you could only stake 32 ETH to get one validator. So that's one of the reasons that there's so many validators today. Today, this is a bit different. We can maybe come back to that. Then you run some beacon to get leader election. Just wanted to mention that I'll have this little icon if something is not perfect, and maybe if someone wants to work on it. The rundown, can be manipulated today. There's various considerations of why it's not been fixed. Maybe Francesco can talk more about that if there's questions. Right. And so what I've been told historically, there was two lines of research. One that tried to mimic this proof of work ghost protocol. And this will be latest message-driven ghost. This is the proof of stake version of it. And there was a line of research to get economic security, and this will be Casper FFG. And so the merge happened in September 22. The beacon chain, as you might probably know, the beacon chain was already running for a while, and then eventually became the consensus engine. We have some slides from some earlier work from my PhD, just to look at, just to say, okay, on this day, you see there was all this hash rate, and then on the merge, this all dropped, and it kind of went to the other proof of work Ethereum forks. And you can see this was the profitability, because there was so much computing power and so many GPUs, right? All the others became unprofitable. Yeah, not much to say there. Okay. Let's dive into a little bit more practical aspects of what we have to consider today. So first of all, validators. As I said initially, you had to stake 32 ETH to become a validator. And so until recently, there was more than 1 million validators. And you can see the blue line here. This has actually been going down. I think today it's less than 900,000 actually. This is despite actually the actual amount of ETH being staked still growing, I believe. But the reason is that you can now consolidate and have validators with more stake. Still, point out 1 million validators is, or 900,000 is still a lot. And you can visit this website to see this consolidation. These validators, I'll have this little icon for them, and then this icon for the clients on which the validators run. The clients, they go through a peer-to-peer network. I'll number the validators here. As I mentioned previously, the clients, they're made up of two layers. There's the historical layer coming from proof of work. So this has, interestingly, the mempool, where if you share your transactions publicly, it will go through the peer-to-peer layer of the execution layer. It has all the state, and all the execution will happen here. There's at least 5 or 6 clients. There's Nethermind, just mentioning Stefano is here from Nethermind. If you want to know more, you can also talk to him. Eventually, with the merge, they added the consensus clients. And here, it has its own peer-to-peer layer with own different peer discovery. It has its, it uses a completely different, gossiping mechanism as well. And here's where the beacon state and the beacon chain live. All right, just to mention.
Quick question.
Yep.
So in my mind, that's not where on the last line, that's not where the mempool lives. Why should I think of that as being encapsulated as part of the execution there?
I think the public mempool, at least, is run by the execution.
Or you just mean
clients.
as far as the way the software is implemented?
Yeah, yeah. That's my understanding that the execution, like these client teams will implement the way transactions are, the mempool is implemented, yeah.
And the blocks are assembled at the consensus layer, right?
No, they're also assembled at the execution layer. There's, I guess, two reasons. Like, one is just historical, that like the execution layer is basically the old chain where like all of this stuff was already happening.
So like execution layer is basically both what I would normally call the consensus and execution layers.
Before the merge, yeah, exactly. And then just the consensus part, which was the Ghost kind of fork choice, was taken out and it was replaced by this other layer. And the other reason is not just historical, is that the state, like the actual execution state, lives there. And so, for example, if you want to process a transaction, you need even just validate that, check that it's valid in the mempool, you still need to have this state. So it's kind of, in a way, the natural place for this to happen compared to the consensus layer. Like whenever there's some kind of interaction with the execution state. So these are kind of, the two reasons, basically.
Yeah, Roger?
Do you have mechanisms in place that no client has too much stake?
Not like in protocol mechanisms. They're more like, there's been like, so these numbers have fluctuated a lot over time based on, I want to say, community awareness of what they are and like attempts to make it more balanced. But there's no like, the protocol doesn't know which client you're running, and so it's all kind of fuzzy.
There's actually from the initial, Yeah, just wanted to add that, we see that the first example was a Prism bug. And I think I've been told that since this bug happened, actually a lot of validators, they tried to switch quickly to fix the bug, or like to not suffer from that. And so actually the share, drops. And so it's kind of dynamic.
Can you go back a slide? Mm-hmm. So here, you first execute and then on consensus. This is how it works on Ethereum?
Currently, yes.
So then you agree only on execution result?
Yeah.
Yeah, so this is changing a little bit in the next fork, but it's, let's say yes for now.
Other questions? All right.
Just thinking the typical SMR abstraction, so the execution layer is the application.
The code will be run by the execution client, yeah.
So for example, consensus doesn't know about what is a transaction.
Yeah, actually literally basically doesn't know, like it can't even parse the transactions. It would actually be nice if it could, but it can't for historical reasons. But yeah, it's not quite as, there isn't like as nice of an abstraction as just like, it's just an application. Like it definitely has a special place in the architecture, but it's also, the consensus doesn't know a lot of the stuff about the execution layer. Like basically this API here is like all that they share, and there's only like a few specific things that go through here.
And they are seeing a point of the consensus layer, or what's the point?
You can get things like, is this finalized, or things like that. You can actually get that from the execution layer as well, but you can get consensus information.
Yeah.
Can you quickly tell what is the type of messages that is received and sent from the first Abyssian point, the second Abyssian point, the first speech layer, the second speech layer?
Oh, okay. I can make a start. Good question. I think so. Here you have the attestations. You have. I think the blocks are actually here, right?
Like they're kind of on both layers. Yeah. There's the execution blocks, but you only share them if you're syncing, like if you're trying to get the historical chain and get a new node up to date. And so that part is just execution content. The consensus blocks exist in the upper layer, and those you kind of share all the time. Like they're like, as the block is being produced, it's going to be sent to people over the gossip in the upper layer. So yeah, but yeah, basically, I mean, the lower layer is really just used for syncing purposes, like basically getting the state effectively, and for transaction mempool. That's the only, I mean, in terms of P2P, those are the only two things that happen in the lower layer. Everything else is above.
Technically, we replace the consensus layer. So we implement that with the RAD, but we replace the consensus layer by a completely different protocol. you only have to call for complete something when you have a confirmation for a block, right? So it doesn't matter the protocol that runs it.
Yeah, you could like basically replace the engine API and the thing above, or sorry, keep the engine API but like implement it with a different thing above.
All right. Yeah, then maybe some numbers on the number of clients. So we've seen the number of validators, this almost 1 million. On the number of clients, of course, is much, much smaller. Here you see we tried to run some crawlers. You see the number here is like 30,000, maybe 40,000. The actual number, so this is kind of everyone that you discovered. The actual numbers that of the clients that actually participate and are reachable is more in the order of like 10,000. All right, so now we have these 10,000 clients that run these 1 million validators. How can they talk to each other? And here I just wanted to point out for the network layer kind of some, trying to put some guiding principles on it, because I think it's definitely something, where we can improve on. So in terms of, and I'm trying to think in terms of crops, which has become like a little bit of a buzzword. So for censorship resistance, one thing that's important is that anyone can run a client. So you can connect and you can you can receive all the attestations you want. You can read the state. You can send transactions. This can of course create problems. Anyone can run the validators, and we've heard about fairness or like from running validators from Australia. I think Ethereum is pretty strong on thinking that everyone should have equal opportunities and should not be punished if they're in Australia. In terms of privacy, for now at least, I think it's also going to stay an important thing that validators should not be linked to their IP addresses, or at least this of course at the moment is possible, as we've heard also yesterday. It's possible to link them, but at least we wouldn't want to exploit that and enforce that in the protocol explicitly. So no structured topology like Turbine. Except if we were to improve the anonymity. And then in terms of security, we want high resilience, and I think especially the last 2 points, there's something where one can improve on. For security, things that come in mind is there's currently anyone can join the network. This is unclear what the security model is. Gossip Sub currently uses peer scoring. It's also unclear how that works from a security perspective. So I think there's a lot of open questions there. Yeah, so ideally we want the validators to be hidden, and now in terms of performance, every validator will have to send votes, and every client should receive these votes. So it's essentially 1 to about 10,000. And if you just did this kind of naively, that would be a lot of messages, right? So one thing that was introduced with the merge is the idea of division of the voting into divisioning into 2 ways. One way is to division it into committees. So in each kind of time instance, you'll have 64 committees, and the committees are associated with subnets. So the idea is that every client now is only in 2 subnets and will only have to care about the data of these 2 subnets. So maybe let me make an example. So if you're validator 2, if you're validator 2 here, this client actually only knows about subnet 39, let's say, but you have been assigned to subnet 62. Okay. So what you have to do is the client has to send your message to that client, to that subnet. That subnet itself will propagate your message only inside that subnet. There'll be an aggregate that will be formed, and then only the aggregate is shared globally. There's a question?
So the subnets are the committees or the 64 committees?
Sorry?
You said there are 64 committees, so the subnet is a committee?
It's not one-to-one, so the subnets are static. So more or less static. So the clients will be in a certain subnet. So that's kind of, the subnet is like the networking abstraction. And the committees will be assigned to a subnet. So it's like, okay, we can say, I don't know if it's the case, but let's say committee 5 of slot X will have to send their data stations to subnet 5. Yeah.
So if I'm a client, I get assigned to a committee?
If you're a validator, if you're a validator, you get assigned to you're in a committee, and that committee could be in any of the subnets.
Assigned to a random subnet?
Yeah.
Like we're using rando or some random subnet?
Yeah, it's like it's using rando.
And the committee is, there's a one-to-one mapping between committee and subnet. It's just that it's changed.
The subnets are like Yann said, they're static. They're just something that you kind of, your network identity binds you to them basically, and you're always in the same one. I mean, there's some rotation, but like for long periods of time, you're in the same one. And the only thing that you need to do with the subnets is publish to them, and so you can also publish in ones that you're not in. Like you send a message to someone in the subnet, and then they take care of spreading it there. And so when you get assigned to a committee as a validator, like for example, let's take that 16, 17, 18, like that's one client, one node that runs a client and exists in a specific subnet, but then it has a bunch of validators, each of which is going to be assigned to a committee, and then it needs to publish things for these validators, if that makes sense. And so yeah, you basically need to, your validator assignments to committees tell you like who you need to talk to in terms of publishing only, if that makes sense.
I apologize. Because I only see here subnets and validators. There's like another thing called committees. Can you again say like, is there a one-to-one mapping? Or like, what's the mapping? Just to I apologize.
Yeah, at in any period of time, a committee is mapped to a subnet. And the mapping basically means like, you should send, if you're in this committee, you should send your messages to that subnet. And then that subnet will take care of propagating them and aggregating them, essentially.
Like a different way of saying this is like the validator is mapped to some subnets.
Yeah, but this rotates, yeah.
Okay, I see.
How do you randomize the mapping?
With this like randomness beacon thing that Yann kind of mentioned before, it's like every epoch or period of time, the Ethereum consensus chain produces like a new random value, that pseudo random value, and this does the mapping.
Yeah, maybe.
I don't want to go too much into the data. Are your tokens still about that P2P, or are you using a different network layer here?
Lib P2P here.
Link P2P.
Yeah.
So they're again using as a sub.
Yes, the P2P is the execution layer.
So the execution layer is a different.
Yeah, it's a different like.
Okay.
Yeah,
so
library.
You know via lib to P2P what subnet you're part of. It's like a topic.
Yeah, it's a topic. Yeah.
Yeah, but the subnets so the clients can pick the subnets they want to be in. They can, I think they can actually unsubscribe from any subnet. That would be a problem if you have aggregator duty. If you have to create an aggregate, you have to be in that subnet to hear all the attestations you want to aggregate. Okay.
Again, for the future, do you plan to do the same for the execution layer? I mean, use the P2P instead of the P2P?
I think it's more like it might be that we stop using libp2p even on the consensus layer.
I don't know if this is going to make it more confusing or or better, but this is kind of a different way maybe of looking at it. So this is kind of, if you connect to a node, what would you see? What does it send to you? Okay, so this node runs 16, 17. So it's this node here. It runs 16, 17, 18, 19. The validators. These are the colors. So it will send to you. So let's say this one validator is 16, will be assigned to different subnets. So this is the attestations. Every 6 minutes, it has to send a vote, and it will always be in a different committee on a different subnet. Okay. So these are all the validators. On top of this, this client is subscribed to 2 subnets, 13, like something like 12 and 13, and it will always relay. It will perform the duty of relaying attestations here, kind of serve as a backbone. And then, okay, the trick is that sometimes when it has to aggregate, so sometimes it has to perform the aggregation, and in that case, it will subscribe to that other subnet where it has to aggregate. So in that committee, actually, it has to aggregate all the data stations, so it will subscribe. And so here you see it kind of receives everything for a while because it's subscribed until it does the aggregate, and then it's gone again, and it only sustains kind of these two. So instead of being, you can imagine this could be full, and you kind of there's less network load because you only care about most of the time you only care about these two subnets, and the rest of the time you only kind of push. Whereas here, this is what you receive. Okay, enough make that makes sense.
What's the physical entity of a node? Because you said a node can have multiple validators. So a machine is a node, and a machine is a validator.
A machine is it runs a client, and on top of this, it can either have 0 validators, or it can have 1, or some have, I think, more than 10,000.
And why would I do that? What's the incentive to run multiple clients on the same machine?
Multiple validators or multiple clients? Multiple validators?
Yeah.
Because this is not much stake, right? You can run 1 validator to 100,000 stake. So if you're a big entity, you want to save on costs. You don't want to run each validator on a different AWS instance, for example.
It's just 32 ETH, right?
Yeah.
So if you have like 64, you have to run 2. You have no choice.
I cannot stake more than 32.
Well,
32 is the minimum.
No, now you can. It used to be that it was the minimum and the maximum. Now you can, but that's kind of this historical thing of.
More, you're forced to divide, right?
Yeah.
Yeah.
Essentially, yeah.
Yeah, unfortunately.
You complicate the system with so many.
Right. Yeah. But still, even today, you can kind of consolidate them together. But you can still decide to run as many as you want on a single machine.
But why today, if you can do more today, why can't they just merge back together if they all belong to the same entity?
There's still a cap to how much stake you can have in a single validator.
Oh, so you still have it to just higher?
Yeah, it's just 2,000.
There is a cap, but the main reason is more like they don't, for the most part, want to do it. Like they just have an operation that works, and
is it somehow add to the security of the protocol?
Sorry?
Does it add to the security?
To have this splitting?
To limit the
to limit some, a bit, yes. Like this 32 ETH bound was not necessary, except for things that people thought that would happen like years ago. But the current bound does have a purpose, and it's basically for like committee sampling security. Like if you made it if you completely remove the bound, it would make this worse, or like make it insecure. So that's the main purpose. But eventually, it's not supposed to be needed. But for now, it is.
It's like my entire stake will not be sampled in the same committee, right? Something like this?
Yeah, something like that, yes.
Yeah, regarding, there is no voting power, right? 1 vote, 32 ETH, right? So even though you have 4 validators, each vote is 1 vote. And it's not, there is no voting power.
There is an effective balance.
Yeah,
Yeah,
there is.
So you can, depending if you've misbehaved or if you've accrued more voting power, it can be slightly higher or lower than 32. Yeah.
But
Pass it back, come back.
But the cap is, I can exceed the cap by creating 2 private keys, right?
Sorry.
I can exceed the cap by creating 2 private keys. Validators are private.
Yeah, so this cap is just about how much a single key can have a stake. It's fine if they're split.
But then how does it factor into security?
It's like the system sees these two as separate, and like all of this you could do without having the cap and just sort of treating a big amount of stake as kind of splittable logically into smaller units. Like for example, for sampling purposes, is just taking the current system and doing this would be extremely complicated, and it just didn't really make sense. So I think it's a lot easier to like try to clean this up later and like basically get rid of the kind of things that make the splitting useful. So yeah, basically simplify what we use committees for. That would be the main basically simplification.
Sorry, I didn't understand now. So you're saying that a validator is a key, right?
Yeah, but it is a key.
So
Yeah.
if I have 4 validators, I have 4 different keys running in the same. Okay.
Yeah.
All right. Yeah, let's continue a little bit with some more networking. So just to say, okay, if you want to go to lab.ifpandaapps.io, you can have kind of a live view of what's happening. Just what I want to point out is currently the slot time is 12 seconds. The first 4 seconds are allocated just to propagate the block. Some high-performance blockchains might laugh at these numbers. Then you have 4 seconds to send attestations, and then another 4 seconds for aggregations, for the aggregates. If you look at the votes, how it looks like is sometimes the block arrives already early, so you can already see some attestations come in. The rest, some clients, they only vote at 4 seconds, so they come in here. You see that there's a lot of kind of gap here to be fully safe, I guess. And then also here would be the aggregates that are propagated. As Francesco said, this is kind of being reworked because this is a big, we could make this better. So there's this ETH P2P effort ongoing. Yeah.
Could you go back to the graph, the little graph?
This one?
That one, yeah. So, do you have an intuition of why the votes arrive so late, like after 2 seconds? Is it like an engineering issue, or is there like a fundamental reason why people would refuse to vote before like half of the? It doesn't seem random to me.
Well, I mean, so this is gossip sub, right? And so first of all, gossip sub it's kind of a primitive that's used for everything, both for the block and the attestations and the aggregate. So this is probably not optimal. Gossip sub itself, I think, had its multiple implementations with multiple programming languages. I think, sometimes, the Go one has an issue. And, I think they've already recently fixed a lot of, or like improved a lot of these softwares. So there's some of this, is my understanding.
But it's really, really sharp.
Do you mean this bump here?
No, the other one.
Sorry. This bump here, my understanding is that it's because some client implementations vote as they receive the block. Kind of, they receive the block, they execute it, they vote. And some others, they always wait until this deadline.
I think you're asking why is it the bump not earlier?
Exactly.
Right. That's because the blocks is not even going to be published until then because people wait as long as they can to make more money, basically.
Okay, that makes sense. And 2 seconds seem to be the optimal point.
I think it's like the point where it's like if you wait longer, it's going to get risky and maybe you're going to lose the block, and so they do it sort of around.
Exactly the question. Yeah. So actually, it's quite interesting that people believe that the optimal theoretic moment is like 2 seconds rather than 3 or 1.5. Right?
Yeah, I think they just try out a lot what wins them blocks, and that's what I guess ended up winning. But
I mean, if you have this observation in mind, why don't cut the time? Why do you let them even to optimize their strategy? If you know 2 seconds is enough for them, just cut it to 2 seconds or 2.5.
Yeah, I mean, it's a bit tricky for a few reasons. Like one of the reasons is there's a big variance in, for example, the max execution time versus the min. Some opcodes can be take a lot longer. They're not all uniform in terms of how much gas versus how much actual kind of CPU time they take. So that's one thing, that the normal block takes 100 milliseconds, but the worst case might take 2 seconds. So that's kind of one reason. That reflects more the median or average block. But there's some security considerations to making it too short. Then, yeah, I mean, another thing is things like, these are mostly fairly sophisticated actors, but then there's also solo stakers that also do building, so that kind of thing. And then, yeah, I mean, the other thing is that it is definitely too much, and it will be, I think, one of the things that is happening, that is going to, for example, happen in the next fork, is a lot of rationalization of what's happening in the slot. So that is a process that's happening, but it's not always immediately straightforward. For example, this variance thing in execution time is really a pretty big security consideration.
What's happening? Is there a rule that you're not going to vote after 4 seconds? Why wouldn't the block producer wait 12 seconds? For 11 seconds?
Yeah, 4 seconds is kind of the cutoff where after that you consider the block to be late. So at 4 seconds you will attest no matter what, and so you will attest to something else if the block hasn't come yet.
So this is enshrined in the protocol that is 4 seconds?
Yeah, I mean, it's not, I guess it's sort of, it's part of the honest validator spec, so it's what the behavior of validator should be. The protocol doesn't really have a way to enforce it, but that's what you're supposed to do. And so that's what the normal clients do.
If you don't see the block, you say...
You vote for what you think right now is the head of the chain, which will not be the thing that you haven't seen.
Are you addressing that producer build separation, is that the name? PBS?
Yes.
In this presentation?
No, sorry.
Yeah, but this is PBS.
Well, so this bump is caused by effective proposer-builder separation existing in the system. Yes.
One more question. What is time zero here? How do you synchronize the time zero?
Yeah, that's a good question. So I mean, time zero is the beginning of the slot. Like the chain has its own kind of heartbeat, and time zero is the beginning. It doesn't actually really have like a meaning in the system in the sense like the actual time that is meaningful is this like deadline for voting. Like 0 is meant to be the point in which you send the block, but it doesn't have any sort of.
No, but it's the same question. If I know 0, I know 4. How do you?
Oh, how do you literally like? I see. I mean, there is an assumption that clocks are synchronized up to like I think half a second or something like that.
You don't worry about screw?
There's like a half a second kind of allowance for that, but not
over time.
more.
You don't feel it over time that they are getting out of sync?
I don't think so. I mean, it seems like not, I guess, but
So just make sure. So this 0 is basically like just the global
yeah.
time 0 in the world. No, it's a specific. Like you have a clock every 12 seconds.
And
For global time. Okay, that's fine.
Eastern or Pacific?
It doesn't matter, but you like on the same clock.
Yeah, I understand. My question was about the screw, and it's not a big deal. Maybe because it's like a long period of time, so they can eat it.
You just run NTP, right?
So this is
Like
I know that measures, right?
the
There's a node measures.
The what?
So at Panda has a node measuring that. The 0 is from each point of view. It's not so sophisticated.
No, but like I mean, the whole system runs on like a fixed schedule, and
This someone measured.
yeah, someone. This is just like someone's
It's like
view
work
of.
of someone.
Yeah, it's someone, but
If my 0 and your 0 have 2 seconds difference,
Yeah.
it's going to be a big issue, right?
yeah, the system in principle like
10 seconds, yes. Right. 1 second.
Like you have to sync with the internet time.
Yeah, that's what I'm saying, because the latency is relatively high. You don't worry about the small differences. 4 seconds is enough to eat over all the small differences. Yeah, that makes sense.
All right, so let's maybe continue with kind of a general idea or general kind of framework of how we can think of the consensus protocol. And so I want to mention here the ebb and flow kind of paradigm. So this very this amazing paper. We have Joachim here in the room that kind of formalized and modeled what Ethereum tried to do with LMD Ghost and Casper FFG. And so I'll try to kind of recap here and say why we think it's important for Ethereum. So the idea of ebb and flow protocols is to have to be comprised of 2 protocols. There's an available protocol and a finality gadget or finality protocol. So I'll note here the little symbols. So the available protocol creates these pink blocks with this blue check mark. This is a confirmation. And the finality gadget outputs these white blocks with this green check mark. This is a finality certificate. Note that the transactions that come in from the mempool, they go into the available protocol. And what is also most noticeable is that the finality gadget, there's a signal that goes back into the available protocol. And here, this is a justification, but it can also be a finalization. Just some signal that goes back. And the reason why this is there is because we want to have this prefix property, right? So the available chain should always be a prefix.
the opposite.
Yeah, it's the opposite. So the finality chain should be a prefix of the available chain. So if the finality gadget finalizes something, the available protocol needs to know it and build on top of that. Okay. Yeah.
Sorry. So me as a client, right, an Ethereum client, what is the difference in the guarantees? Like I understand finality gadget probably means confirmation will never change again, right? The availability, what does this, do I care about it as a client? Does it give me anything, any meaningful information?
So I think so far no, but there's a new effort. So very recently there's a new effort to kind of push this signal as well. We call it the fast confirmation rule. And so yeah, hopefully this you can get much faster than this one.
And this will be, the signal will be most likely this is the thing that's going to be soon finalized?
Yes,
Yeah.
it's going to be in this very precise model. if this model is true, then it will be finalized.
If the network is synchronous and the majority is honest among the ones that are crashed, then this is confirmed and will not be returned. That would be the bug.
Yeah. In fact, we have a quick slide on this. It's not going to be the majority. There's a higher assumption on the adversary resilience. It's going to be more like 80% being honest. But under these stronger consumptions and synchrony, as Joachim said, then
if I'm client and I'm okay with this assumption, I can take it, right?
Yeah.
I don't need to wait on this.
Exactly. But there's the other differences. Like this is a local. So to get this, you have to run your own client, and you have to be connected to all the subnets. You have to listen to all the stations, and then you can see this for yourself. But you cannot convince someone else that this happened, right? All right, so the different way to look at it is we have this available chain that produces blocks, and ideally once they're confirmed, they'll be finalized by this finality chain. We have these two models that I introduced before. And just to briefly talk about the advantages of this construction. So first of all, it can kind of circumvent the cap theorem by having one chain that is available but not safe under asynchrony, and the other being safe under asynchrony but not available. Okay, so this is kind of going back to Itai's peacetime wartime reference. That available chain itself, it can continuously pump out blocks ideally, and very importantly, it brings this higher adversary resilience. So ideally, we want to carry this 50% resilience under synchrony. This will also apply to these blocks as well. And so it will make the whole systems more safe. Something else that might be interesting of the available chain, we think this for post-quantum transitions, this might be maybe easier to do in the available chain. For the available chain, for the finality chain, we get the immediate thing we get is economic security and slashing. And maybe at the end, if we have time, we can discuss kind of the slot length versus time to finality trade-off, which turns out to also be good in this model.
So the post-quantum, that's because you don't need signature aggregation for the available chain?
That's right, yeah. Because the idea would be to maybe sample validators here, and so there's less load, less stations, and so these wouldn't have to be aggregated.
Yeah, you don't run the finality chain for every block, do you?
No, there's checkpoints. Yeah.
Like so literally you're creating checkpoints on the.
Yeah. If you want to read more about the reasons why we want this construction, look over a great post on this. And then before I hand off to Francesco, maybe I'll briefly say a little bit about the current protocol and give you some ideas on how LMD Ghost and Casper FFG look like on a high level. So this is a perfect question you ask with the checkpoints. So in the big picture, we have these epochs. They're comprised of 32 slots. Each slot is 12 seconds. And so every validator will send a vote once per epoch. So if you have the whole big 1 million validators, 1 over 32 of them will be selected for the first slot, and they'll have to send their attestations during that first slot. And so this is kind of the time division, and then we have the division into subnets. So this 1 over 32 will further be split into 64 committees, into 64 subnets, and so this is kind of what happens in one slot. So the validators will send their LMD Ghost vote. So they will attest to what they see as the head of the chain. This is kind of a brief, I'll maybe not go too much into it. But essentially, you send a vote for what you see as the tip of your chain. And the ghost part, so this is, you care about, so LMD stands for latest message driven. So for every of these validators, you'll only look at their latest hour, the latest message. So if you look at this, we can run the fork choice on this example. So imagine these are all the latest votes you've seen, and these are the blocks. So you'll look at the heaviest subtree according to these yellow votes. So first here at the fork choice, you'll pick this one. Then you'll pick this one because it's 2 votes versus 1. and then this will become the tip of your chain. LMD Ghost contains, it provides a k-deep confirmation, as we've seen as is, standard also in proof of work. So if you have or kappa deep, I should say. So if you're kappa deep, you can you get this blue check mark, and this is what I mentioned before. This is a new work done by some colleagues of mine, the fast confirmation rule. So kind of backfitting a confirmation rule for LMD Ghost that works actually in the same slot under a certain model, which is a higher assumption on the adversary and synchrony. This is highly non-trivial, so I don't want to go too much into detail. Just saying that historically, if you consider the network, the way, of course, historically no one had an incentive to attack it, but it would never have, been unsafe, and it would almost always have, given the confirmation in a single slot. That's this plot that shows like 92% of the time, or even more. It gives you an immediate confirmation. Then we have checkpoints. And so at the same time as you send your LMD Ghost votes, you'll send your FFG votes that will make up the finality gadget. And this is kind of the end of it. I just want to mention here, I'll not go into detail because this is kind of just essentially standard Tendermint, or the extension is just Casper FFG. So if you get, with the difference that instead of voting just for a target, you'll vote for both the target and the source for accountability reasons. And so if you have 2/3 of the votes that create this link, this is going to become a majority link and will justify this block. And if you have the next, also 2/3 from the justified to a non-justified, it will justify this one and finalize this checkpoint. Perfect. Yeah, that's it for me for now.
All right. Okay. Can you hear me right? Okay. Yeah. Thanks, Yann, for the introduction. I think we should have most of the concept that we need to go through the rest. So this is going to be a bit different from now. It's going to be a bit more into some details rather than zoomed out. So the kind of first thing I would like to talk about is basically diving a bit more into this latest thing that Yann introduced, the available chain. Actually, already you can tell there's something a bit weird about this model that we had to use for fast confirmation, that we need such a high this 80% number or even more. And yeah, it kind of tells you there's something weird there, this should be just 50%. And so yeah, I'll be talking about security or insecurity of LMD Ghost and kind of how to think about that and how to fix it. So first of all, quick repeating, also just because it's a slightly different visual language, but sort of what Yann said. So LMD Ghost is a fourth choice, so it's a way to go from a block tree and some votes to a head of the chain, but it's also a protocol, and the protocol is very simple. It's just basically someone proposes a block and then everyone votes. And the way both of these actions happen is that they run the equally named fourth choice. So at any of those two times, like proposing and attesting, you would run the fourth choice to tell you what is the right thing to do an action on. So if I want to propose a block, I run the fourth choice. It tells me this is the head of the chain and I want to extend that. And same for voting, basically. So we want to talk about security.
On fixed times?
So I guess the correspondence here to the Ethereum slot would be that, okay, there's also another delta that is for aggregating, but kind of ignoring that, then it maps to this structure basically.
But this is some global time.
Yeah, I mean you could do it differently, but then mapping to Ethereum, it would be with a global time. Let's quickly define what is security for LMD Ghost, and we're working with this sleepy model that we've kind of talked about for the available chain. So less than 50% attacker among the awake validators, and in principle you could have a lot of asleep validators, or at least that's what we want. And usual safety and liveness thing definitions in this model. So there's one specific attack that basically tells you LMD Ghost doesn't work, doesn't actually satisfy in any possible way those security definitions. And it's basically this balancing attack. So imagine green is going to be honest, good, red is bad, obviously. So someone creates this initial kind of split situation. The honest votes are kind of split between two chains. And the way that this happens is basically that a malicious block, like these red block or both of the red blocks, are published around the voting deadline. So it's published in such a way that half of the validators see it before the voting deadline and half after the voting deadline, so that they end up voting for different blocks. Yeah, this like crown thing is going to be the head of the chain. So by like a hair, the C block is the head of the chain because it has slightly more weight. And so people will build on that. There's an honest block that extends it. Now the adversary kind of plays the same game, but with votes. It has like a little bit of voting power. It publishes the votes in this like, again, like kind of targeted way, like around the deadline. And now it pushes the voting power towards the majority on the above branch. And so it pushes basically B to be the head of the chain. And so now this causes validators to vote. Again, so this was done in such a way that some of the validators saw these like 3 adversarial votes and some didn't. And so we kind of repeat the same situation of like, now we're split between the 2 branches. And this can go on, the adversary can keep playing the same game, basically. In principle, forever, if there's, if they succeed at doing this like targeted publishing in every slot. And eventually, if they want to, they can kind of conclude the attack by basically just stopping, letting the force choice collapse on one of the 2 sides, and now everyone is on that side, and whatever happened on the above branch is gone and reorged, and that could have been like a while, could have been like a long period of time. And so this basically already tells us that
just for reference, so is this like a relatively new thing, or is it like part of the saga of...
It's a part of the saga, so this is exactly like kind of the central attack of the things that they were showing. So it's very much historical context still. So yeah, basically this attack essentially shows like LMD Ghost is fully insecure in the way that it's been specified so far. It doesn't matter what confirmation rule you choose, it cannot possibly be secure. The reason is basically that if it's live, at some point it will confirm something. So for example, it will confirm this block B, and then the adversary can just collapse the attack on the other branch, and then eventually the other branch will confirm something, and so it will have a safety violation. And so yeah, that's the kind of the horrible premise that we have something completely broken. And so from there we want to understand, okay, how do we actually construct like a secure available chain? And so one note is that, okay, we could have just used the existing secure available chain. Like the original reason why the sleepy paper was written is that there was a protocol that seemed to work under these conditions, and it was longest chain. And in fact, it is secure in that model. And the reason that we're kind of not fine with it is mainly this like constant latency or lack of constant latency part. So there's no voting process, or like the voting process is just publishing a block. And so yeah, basically you're kind of forced to have this kappa deep confirmation where you just wait for a while, like the classic Bitcoin, wait for some blocks confirmation. And so that's not really that is basically not something we'd like. There's also this deterministic versus probabilistic safety part, but that's maybe less important to different people. But yeah, the bottom line is like we have proof of stake, we have this like ability to process a lot of votes in parallel. There's no reason that we should have we shouldn't have constant latency. And so the basically most basic idea of like how to try to approach this problem of fixing LMD Ghost is that you basically want to break this balancing attack, because that seems to be like the thing that's actually making everything, or like the intuition is that that's really the problem. It's not just like one attack, it sort of epitomizes like everything that's wrong with the protocol. And so the idea is basically to say, okay, can we somehow use honest proposers as like a synchronization point, like as a way to prevent this like sneaky, getting votes on to be split between the 2 forks. So we kind of start from a situation where we have the balanced chain, like the 2 branches, and the votes being split. Now an honest proposer comes and makes this like green block on one of the 2 sides. What we would like is this, so that everything collapses to that side, so that it's not just the adversary that can do this, but even an honest proposer can basically force this, and at least temporarily like break this balancing. And so the general idea is just this proposer-driven synchronization. A specific way to do this that we didn't actually come up with. There's a paper that did this that we're not aware of, but either way, like this idea was existed. to basically add like a little bit of extra, another delta essentially to this like propose a test protocol, and to do some kind of synchronization thing with this delta. So we call this phase freeze. There's like this eye that's meant to say validators are sort of observing what's happening at this point. So they, at that point in time, they freeze their view of what happened in this moment, and then they do something with that. And does something looks basically like this. So here we have 2 slots. So here again we have now like a 3 delta kind of slot for this new LMD ghost. So this is one slot, this is the other slot. It's again, a block comes, then there's attestations. At this point you will observe, like this is like a specific validator is observing this, like call it V for view. So this is just whichever votes you've seen, essentially, roughly speaking. And the important thing is that you keep forwarding. So you kind of freeze that you've seen these things. You can record the time, timestamps or whatever, however you want to do this, but you keep forwarding votes. And the idea is that the proposer in that way should have a view that's kind of a superset of yours by this point. So it should have some bigger view of votes. And the proposer will basically point to this and say, like, look, this is what I saw when I proposed the block. This is what kind of made me do what I did. Like, I used this view to run the fork choice. It, landed me on some part of the block tree. Can you get to the same part as me? And what you would do is then at this new attestation point is that you would basically take these 2 things and merge them together, basically roughly do a union. And the hope, and which would actually be true if if synchrony holds, is that you end up with the same exact thing as the proposer. So there's no, oh, I have 51 and you have 49. It's like you actually see the same thing as the proposer did, and you can end up with the same outcome. So you run the fork choice and you end up attesting to the same thing that the proposer proposed. And yeah, I mean, formally it's just this. At the end of the day, it's just counting on this containment, which is just through synchrony, and then then eventually you'll end up with this merged view that's the same as the proposer. So that's one way to do this, but and I'm kind of mentioning specifically that one because I'm the one that I'm most familiar with, the one that we're thinking we might actually use in the future. But it turns out that it's not a very it's not the only way to do it, but it's kind of there's the other ways to do it look quite similar, at least the ones that people have come up with, in the sense that they still use this like proposer synchronization idea. And so they all kind of end up adding some delta and do something with that to do some synchronization. So there's specifically this idea that came up in this like quite nice paper that actually was the first one to have a constant latency in the Sleepy model. So this thing that we said longest chain doesn't provide, this paper was the first to say like, oh, you can actually do it. So had this like existence proof. And it precisely used this technique, like this time shifted quorum thing, which is very much doing some kind of synchronization in a similar way. Then there was some follow-up that improved bounds, like building on this, and there was another paper that we had that was kind of also building on this and doing similar things. But yeah, the point is like there's a lot of work that is doing things that are not view merge but similar to view merge and kind of achieving good results. What we would like at the end of the day, or what we hope, is that we have this so that LMD Ghost with view merge is actually secure. So once we've added just this one little piece, it's secure with the kappa deep confirmation rule. So for now, we'll still stick to not having constant latency just for the purpose of this talk. It's kind of a bit easier to justify that it's secure with respect to this rule. And another thing is that what's actually true is that we're not quite yet at security in the Sleepy model. So what we get from just taking LMD Ghost and adding this synchronization is that we get security in the normal synchronous model, so where everyone is awake. We don't have fully fluctuating participation. And it's actually very easy to see why this is true, and so I'll like briefly go through the result. The key thing is basically this property, reorg resilience, that it's a bit hard to like say exactly formally. It's not like safety or liveness that it's like a very universal property, but it makes sense when you phrase it, at least for this protocol. And it basically says that once an honest proposer proposes something, their contribution actually stays in the chain. So before we even get to why this is true, what we can see very easily is that if we do have that property, then we immediately have security for the kappa deep confirmation rule. The reason basically being that once you go kappa back, there's at least, with high probability, one honest leader, and this leader basically collapses the problems in the chain, essentially. So things can be messy afterwards, but before we're down to like a single chain that everyone agrees on, and so the prefix then becomes safe. And yeah, I mean, that's, I guess, already said that, yeah, so here we're still talking about non-constant latency, and we can do better, but it's just for the purpose of this, I'm not gonna talk about that in detail. So it turns out real resilient is also like very easy to see more or less why it works now. The reason is basically just that once you have a majority of participants that are all on some subtree, so you can maybe remember like LMD Ghost works by comparing subtrees. So at this point you're trying to decide between, like the fourth choice is literally that, you know, here there's a fork and you're choosing which branch you're going with. And when you do that, you're comparing a subtree against another subtree by just checking like how much weight does the whole subtree have versus the other one. And so when you have a majority of the weight on one subtree, it's always gonna, and like the head will always land on that subtree. Basically, it's gonna win every comparison. Like you know, repeatedly will do comparisons, but a subtree that has a majority can never lose one, essentially. And so, so that's for a majority in general. But once we have a majority that is comprised of honest validators, so like a green majority, this is sticky in some sense. So once you have that for some slot n, let's say, then it perpetuates itself in the next slot. Like at this point, we have a majority, everyone knows it, so they see that, you know, so we continue, maybe something else gets added to the chain. People will run the fourth choice with the previous votes, and they will still end up somewhere here. And so they still vote somewhere here. And so we basically have, you know, this induction that you know, forever people will kind of be stuck to this subtree. So for example, if everyone voted for B, then B can never be reorged because we'll always stick to a subtree that contains B, basically. And yeah, and so on and so on. And basically what we didn't, so this was actually true for LMD Ghost in general. This doesn't depend on the synchronization properties, just like a general property of LMD Ghost. Like LMD Ghost is good once it does make a decision in some sense, or like once it kind of collapses everyone onto some subtree, LMD Ghost does have this sticky property always. And what we get by doing this synchronization is that we get the initial thing. Like we actually do manage to kind of collapse everyone onto one side. And so yeah, basically we, specifically once we get an honest block, so some guy shows up, does the synchronization, everyone is on that side, and now we have the base case of this kind of induction, and now no one is ever going to be able to leave the subtree of B.
Can I ask?
Yeah.
So at this point, it's not finality yet, right?
No, it's not finality. Yeah, well, everything that I'm saying is assuming synchrony.
It's still probabilistic so far, or?
So the probabilistic part is this one. So when this proposer shows up that does the collapsing, that does the synchronization, gets everyone the same size, this is not probabilistic. It is dependent on synchrony. So this is only true if then, you know, people see this and then in the next slot they, you know, see those previous. So yeah, like
under synchrony assumption, this is already final.
Yeah, it's final in a deterministic way.
I see.
Actually, so just a quick thing, it turns out that actually for LMD Ghost specifically, synchrony is not even required. Like you can actually get a synchronous safety out of LMD Ghost. But yeah, anyway, sorry, go ahead.
Go back to that K confirmation of confirmation. This is still probabilistic, is that?
Yeah, so this is probabilistic, yes.
So at what point it became, so it's the real merge
so it's...
so if this is still probabilistic, at what point it became deterministic?
So the thing is that here, we're saying that there's a majority of honest votes, and from outside you cannot observe this. Like you can observe that there's a majority, you cannot observe that there's a majority of honest votes because you don't know who's honest. And so if you could observe this, then that would be deterministic, but you cannot. And so what you can observe is just, well, a lot of time has passed. Hopefully there was an honest proposer that forced that situation to happen.
Okay, so I'm trying to understand.
Yeah.
Better. So does that mean that just here back to randomness, there will be a point where there is honest majority there, even if we can't tell with who there is.
Yeah.
In that sense, it is with probably one, it's going to happen, but we don't know when it's going to happen.
Yeah, exactly. So it's basically what you would choose this for is that so every slot should have a probability 1/2 of having an honest proposer, and so if you want that the security guarantee is like 2 to the minus kappa, then you would choose this to be kappa. Basically, it's your like security parameter.
Okay, thanks.
Can you move to the next one, please? So if someone votes on B here and then votes for the other branch, is this considered an equivocation?
No, because in principle you don't know why they did it. Like it might be that from their perspective it looked like you don't know that they see a majority. So
this is an analysis for someone seeing everything from the
yeah, like you would have to know that these are like honest validators that are doing this. So as I was saying, like as it turns out, you can actually make it a accountably safe protocol, even LMD Ghost. People have done it. Like there's a paper that basically does this, and it's based on basically the same sort of reasoning. But we're not sort of interested in using it that way. We're kind of interested in it as an available protocol. And yeah, I mean, if you try to think about it in this like as an accountably safe, like a synchronously safe protocol, you anyway will need to, will run into like this availability finality dilemmas. You will anyway need to kind of deal with 2 different chains. So it's not that it's like a magic bullet to think about it that way. But it turns out that you can actually get stronger guarantees just from this protocol with a different confirmation rule, obviously. Okay. So yeah, right. So yeah, that was basically it. Like if we have.
We should break soon.
Okay.
This is the right time.
Right. Yeah, maybe let's just break here. I think there's a few more things in the available chain part, but the second part is a bit lighter, so maybe it makes sense to just stop here and then restart from here.